All right, good morning, good afternoon. Welcome back. Our Fearless 7. All right, well, any questions? So again, if you didn't turn in your homework, you got 4 minutes to turn it in late. So hop onto Canvas and turn that in if you didn't already. And I will grade this over the next couple of days and we'll talk through it on Wednesday. Permutations, combinations, counting, arguments. I like that line triangle problem. Yeah, I think that's a good one too. Interesting things you can do with combinations and permutations. Yeah, I had to think about that one a little bit too, and then it's definitely interesting when you suddenly see it. It's a fun kind of problem. Yeah, one is like Pluto, right? It should be prime, but it's just decided that it's not going to be prime. So that's too bad for one. It probably breaks things if we let one be prime, though. Actually, I don't think it does. It just makes other things take more work.
Hey, so I have a question.
Yeah.
If we wanted to return the largest value of like one of the primes without using a global, would we have to return a structure and like do a pointer and stuff? Or like, because we're returning, at least the way I set it up is I returned if something was prime. And so if I also wanted to return if that number was bigger than the last thing found, I'd have to like send a structure, I think.
What do you mean by bigger than the last thing found?
Yeah, so I was like curious on what was the biggest prime that we encountered. Or like the biggest, I don't know. I was just looking through it and I was like, wow, some of these primes, like we had to go a lot of checks before we
Yeah.
first prime. And so I was just curious what that was. And so I was just trying to figure out the code for it. And the best way I could think to do would be a global to pass it through that other function. But maybe I just need to think more about it.
A global is certainly the easiest, and that's what comes to mind for me because, you know, wherever you encounter this thing, you want to record, hey, I found a prime of 61, or whatever it turns out to be. That would be a good use for a global. Unfortunately, sometimes globals are demonized, and I've heard teachers in other courses say, you know, if you use any global variables in your code, you'll get a 0 automatically. So if that's the case, you could pass a variable to your prime function, right? In addition to the number that you're testing, you could pass the address of something that holds the largest prime found so far. And then, you know, if your tester finds that your number is prime, you go ahead and update that. Or you could return a structure, like I think you were suggesting. Instead of just returning an integer, you could have a structure that has a flag and also, you know, the current largest. All of those to me are kind of silly ways to avoid a global, when in fact a global is really what's kind of called for there. And just like go-tos, you know, globals exist. Most of main memory is effectively global variables when you get to the assembly language level. So if we don't get too dogmatic, sometimes it makes sense to just, you know, have a largest prime found global variable. What was the largest prime anyone found? I saw some 61s.
Well, I was using 1 as a prime, so I can't.
Okay. Well, using 1 as a prime, what was the largest prime you encountered?
I didn't code it yet, but I let me look.
Okay. Oh, 147. Wow, cool. Okay. Yeah, I looked at the beginning and the end of the lists. I didn't check every entry, obviously. That's pretty cool. If you go to Wikipedia and you do some looking at Goldbach's conjecture, there's a lot of work that's been done on it, and people have put some ridiculous bounds on criteria for a counterexample, and it's been shown that, you know, if there is an even number that breaks Goldbach's conjecture, it's got some ridiculous characteristics, including a really huge size. And it's not that we've tested every even number up to that point. It's just, you know, mathematical trickery for demonstrating these bounds. Hey, glad you're here. No worries about being late. So yeah, it's an interesting problem, and like so many things in this area, it's a deceptively simple sounding problem, right? Can you write an even as a sum of two primes, and it exposes some very rich areas of mathematics. So that's fun. Something else I was gonna say around that topic. 167, cool. And a surprisingly large number of evens can be written by just using the first few primes, right? You know, 3 plus something, 5 plus something, 7 plus something. That gets you the majority. Oh, someone found a 181, cool. So, but then every now and then there's you know, an even number that takes some really big primes. And there's a lot of really deep mathematics and discovery you can do around relatively simple questions of primes. For example, looking at how many primes divide a number can get you into some fascinating million-dollar questions around the zeta function and things like that. So yeah, this is all cool stuff. All right. Well, so we're going to switch gears again. We were talking about counting and combinations, permutations, product sum rules, inclusion, exclusion, pigeonhole principle last week. So we're going to change gears again today and talk about some graph theory. And graph theory is another one of these areas that pops up a lot in computer science. And there's some pretty basic questions in graph theory that are easy to describe, easy to understand, very difficult, if not impossible, to find closed form solutions for, but that we can manage with computers to get pretty good solutions for. The kind of quintessential problem of this nature is the traveling salesperson problem, so TS. And we'll touch on TS at the end of the course. We'll talk about it this week, but we'll come back to it at the end of next week. In terms of computability and something called NP completeness. So let's develop some subjects around graphs and graph theory. And so we're going to need some definitions as usual. And some of this will be pretty formal, but some of it I'm just going to wave my hands at, because you can get a lot further with hand waving sometimes. And we don't need, you know, extreme rigor in this. So first hand wavy definition, what's a graph? Well, it's a bunch of dots connected together with points. Okay. We could put, you know, a whole textbook of formulae and definitions, but it's a bunch of dots connected by points. By lines, right? That's basically what a graph is. So we'll start with that, and we'll add some more detail. But that's a graph. This is a graph. This whole thing with two pictures here is also a graph. This is also a graph. All right. So what do these things have in common? Well, a bunch of points connected together by lines. Sometimes, you know, all the points in our graph are interconnected so that from any one point we can get to another point. That's called a connected graph. Sometimes, you know, there's some points you can't get to from some other points. That's not a connected graph, but it's still technically a graph. So these points are called vertices, and these lines are called edges. And so we'll stick with that. And sometimes vertices are called nodes, but I'll try to stick with the vertices. And sometimes, you know, a vertex will have a single edge coming out of it. Sometimes it has two edges. Sometimes it might have three edges. And sometimes there might be a pair of vertices connected by more than one edge. For example, there's three edges connecting these two vertices together. That's totally legal. But it's a different kind of graph if we allow these kinds of multiplicities. Sometimes our edges have arrows on them, indicating a directionality. In which case it might make a little more sense to have two edges between a pair of vertices. So in this case there's an edge from here to there, and there's also an edge from there to here. And there's an edge from there to this node. And so we can have a directed graph where edges have directions, or we can have an undirected graph where they're just, you know, lines connecting points. Sometimes these are just plain edges, or sometimes they have values or weights associated with them. So we can have a weighted or an unweighted graph. And these weights could represent distance or cost or time or something else. And sometimes these weights could be negative, or sometimes they're restricted to just being positive. And in every one of these situations, things change, sometimes subtly, sometimes significantly. There are problems we can solve for a weighted graph, as long as the weights are all positive, that are very much more difficult to solve if we allow negative weights. Ooh, someone found a 463. Awesome. All right, so let's add a little bit of formality. So a graph is an ordered pair, a tuple, of two sets V and E. This is a non-empty set of vertices. And this is a set of edges, which could be empty. So, you know, I could go boink, boink, boink. That's a perfectly fine graph. Three vertices, no edges. And each edge connects one or two vertices. And those vertices are called endpoints. So nothing too alarming here, definition-wise. And we can use graphs to represent a number of things. For example, we could have a series of landmarks with roads connecting them. So these could represent locations in one city, and these could represent locations in another city, very small city. And these might be roadways connecting them. And you can see there's one road connecting this set of cities to that set of cities. And we might weight these edges with distance. So, you know, this is 1 mile and 1.5 miles and 2.3 miles, and this is 10.7 miles and 2112.5. So we could represent distance like this. We could make an acquaintance graph. We could have, persons A, B, C, D, and E, and we could draw an edge connecting any two people who are acquainted with one another, any two people who know each other. So here, everybody knows person B, but nobody knows anybody else. And here's person G who doesn't know B directly, but knows B indirectly through person D. And so we can start to ask, is there a path from one vertex to another? In other words, is there a collection of people through which person G knows person B? Well, that's equivalent to saying, is there a way starting from person G to follow edges and eventually reach person B? And that collection of edges would be called a path. And in our town example, if there were one-way streets, maybe this street is one way, this could be a directed graph. And, maybe all of these are two-way, and so on. We can model computer networks with graphs. And so I don't even want to try to draw my home network, but you might have a series of machines connected to a router, and maybe some kind of local area, a LAN with Cat5 cable with some nodes connected to that, and that's also connected to the router. And where does this router go? Well, it goes out to Comcast somewhere, and from there there's links going to other parts of the trunk, and so there's a big network. And if you have say a network graph like this, you can start to do analysis. For example, suppose that this link goes down. Well, is there still a path from this machine here to this machine over here where Netflix is streaming their content, right? What happens if this link goes down? If I have time weights on here, what happens to the transmission time if I find a different route from here to here by not following this link because this link went down? So you can do lots of analysis. Yeah, we could have a LAN party. You can do lots of analysis on problems like this from the perspective of graph theory. All right, so graph, it's a pair of VE, vertices and edges. Google Maps is an ultimate graph theory exercise. We will get to some of that. We'll get to something called Dijkstra's algorithm at the end of the week, which is a pretty cool little algorithm to know for finding shortest paths. I know Google does something much fancier than Dijkstra, but it's still a cool algorithm. All right, if we have a directed graph, right, a graph where we have directions associated with each of these. In a directed graph, 181 plus 5,263,000. That's pretty cool. I wonder what the smallest even is that forces you to have a 4-digit prime. And it might be smaller than 5 million. Yeah, rabbit holes. In a directed graph, each edge can be written as an ordered pair UV, and it looks basically like this. Right, we have an edge going from U to V. All right, some more definitions. And I'm not always going to write this in a graph business, but I'll do this for the first few times. So in a graph G, which is this ordered pair of V, E of vertices and edges, yes, you could write a program for that. In fact, you've already got a program for that. You just need to change your main program. So, yeah, see what the smallest even is for which you need a 4-digit prime to write it as a sum. So in a graph G, comprised of vertices and edges, two vertices, U and V, are called adjacent. If there is an edge, E contained in E, that connects U and V. So again, hand wavy, B and E are adjacent, B and C are adjacent, B and G are not adjacent. There's no single edge connecting them. And if this is the case, we can say E is incident to U and V. Just means it connects them. All right, N of V is the neighborhood of V. Which is the set of all points in the collection of vertices such that U is connected to V. And if U is connected to V, we can say U is a neighbor of V. And so V is a neighbor of U. So N of V is the set of all neighbors of V. So the neighborhood of B would be A, E, C, and D. The neighborhood of D would be B and G. The neighborhood of C would be just B. Cool, nice analysis. 523, that's good. I didn't mean you had to do this right now, though. But that's cool. All right, so we're coming up to our first theorems. Neighborhood of a vertex is the set of all vertices that are connected to that vertex. The degree of a vertex V, which we write as degree of V, is the number of edges connected to V, or incident to V. So the degree of A is 1 because there's one edge. The degree of D is 2. The degree of B would be 4. Yeah, no, I'd be coding it up too if I wasn't teaching. All right. An interesting thing about degree, though, loops count twice. So if we had an edge like this, the degree of A would actually be equal to 3. It's once for this edge, but this edge counts twice. That's going to be important. All right, so let's pick on this graph here. Degree of A is equal to 3. The degree of B is what? Four, because we got 1, 2, 3, 4 edges. Degree of E is 1, the degree of C is 1, the degree of D is 2, and the degree of G is 1. Cool. Why does A have a loop but C doesn't? Just because I didn't draw a loop there. This is a random graph. That's okay. Yeah, it's just a graph I made up. So C only has one edge coming out of it. It's funny that Sorry, say again?
Can you go back to the definitions page real quick?
This one?
Yeah.
Okay. It's funny that keyboards still have caps lock on them.
And the other one, my bad.
That one? Or this one?
I got it.
Okay, cool. All right, so we can find the degree of each vertex. So here's a theorem. If we sum up over all of the vertices in V, the degree of each vertex, we get twice the cardinality of the set of edges. So in this case, what do we get if we add the degrees? 3 plus 4 is 7, 8, 9, 11, 12. And how many edges do we have in our graph? 1, 2, 3, 4, 5, 6. And the sum of the degrees is exactly twice the number of edges. And this is always the case. We're talking about undirected graphs so far. So we've just got edges without arrows on them. So the sum of the degrees is always twice the number of edges. And how could we prove that if we had to? What kind of mechanism might we use to prove this? Well, let's think about it intuitively. This is cardinality of the set E. Remember, E is a set of edges. And so this is just the number of elements in that set. So once I have my graph here, suppose I add another edge somewhere. if I draw my edge, it's going to begin at some vertex, which means the degree at that vertex will increase by 1. And this edge is going to end at some other vertex. Now, it could end here, or here, or here, or here, or even back at E. But wherever it ends, the degree of that vertex is also going to go up by 1. So by adding one more edge, I'm guaranteed the degree, the sum of my degrees goes up by 2. So how would I put that together into a formal proof? What would be the mechanism I'd use? We can use mathematical induction, absolutely. We could induct on the number of vertices. And you have to do a bit of work to show a base case that for one vertex this is guaranteed to be true. But then you can argue that, you know, adding another, or we could induct on the number of edges. So show this is true for something with no edges, and then just make this argument that when you add an edge, there's 2 nodes, possibly the same, whose degree goes up by 1, so the sum increases by 2. And it's pretty straightforward after that. Alright, you know what a corollary is? It's like a small theorem. It's usually not as grandiose as a theorem, but it's usually a fairly direct consequence of another theorem. And so there's a corollary we can state here. Which says the number of vertices with odd degree is even. So how many vertices here had odd degree? 1, 2, 3, 4. 4 is an even number. This corollary says we can't have an undirected graph like this where, for example, 5 vertices had odd degree, or 3 vertices had odd degree. It's always got to be an even number. Why is that? Why would we only be able to have an even number of vertices with odd degree? Think about modular arithmetic. These are true for every connection there are 2 vertices, because we get an even number when we add 2 odds. And in particular, if you add an odd number of odds, you get an odd number. So if we were to write these down in terms of you know, modular 2, so even numbers are congruent to 0, odd numbers are congruent to 1. If you have an odd number of vertices with an odd degree, that sum is going to be an odd number, and an odd number cannot be twice an integer. So it cannot be twice the number of edges. So we get this nice little corollary almost for free out of this theorem. That when you have a graph and you look at the degree of each vertex, and you pull out just the ones with an odd degree, that's got to be an even number of such vertices. That may or may not be useful later in life. We never know. All right, so let's go back to directed graphs. And let's just look at a situation, 2 vertices u and v, and we have an edge going from u to v. All right, so some terminology. U is adjacent to V. And we would say V is adjacent from U. U is the initial vertex, and V is the terminal vertex. Yeah, this will get state diagrammy for sure. And we can, you know, treat state diagrams as graphs. I mean, they are graphs. And that's an interesting way to analyze digital circuits. For example, we might want to know, you know, what's the shortest path from this state to that state. And you know, maybe you can look at it and you can figure it out, but if your machine has 5,000 possible states with, you know, 1,000,000 edges, it's hard to just kind of look at that and say, oh, here's how I can get from this state to that state. But if you can do some analysis, you could say, oh, follow these edges, right? And that gets you there in 25 hops. All right, so for directed graphs, this notion of degree is a little more complex. So we have two types of degree. So degree minus, this is the in degree. Which is equal to the number of edges. I'll just say ending at U. So the number of edges whose terminal vertex is U. If you like, the number of arrows going into that vertex. Degree plus is called the out degree and equals the number of edges leaving a vertex, or whose initial vertex is U. So it's the number of arrows going out. So we can start to label these. So what's the in degree of vertex A? It's the number of edges ending at A. Yep, it's just this one edge over here. And what's the out degree? That's a 2. 2 edges coming out. So nothing terribly heavy. So the in degree here, we have 2 edges coming in and we have 1 edge coming out. Vertex C, we have 1 edge coming in and 2 edges coming out. Did I switch up my definitions? Minus is coming in. Yep, I messed these up already. All right, the in degree of D, we have 1 edge coming in, we have no edges going out. All right, and we have a corresponding theorem. So we have a graph with vertices V and edges E. If we sum across all the vertices in that set V, the sum of the in degree is the same as the sum of the out degree, which is the same as the number of edges in your graph. So add up the incoming degrees. We have 1, 2, 3, 5. So that's the sum of the in degrees. If we add the out degrees, that's 2, 4, 0, and 1 is 5. And 5 is 1, 2, 3, 4, 5, the number of edges in the graph. So that's a cool little theorem. All right, so there are lots of different graphs out there, but it's useful to have some basic graphs that we can use for examples and as building blocks. So let me describe some basic examples. So complete graph. Complete graph of n vertices, and this is called Kn, and it's a graph where you have every possible edge that you could have between any pair of vertices, so it's completely connected. So K1 just looks like a dot. K2 is just two vertices connected. K3 will be three vertices connected in a triangle. K4, we'd have four vertices and connections between every pair of them. So it looks like that, and so on. So those are complete graphs. Cycles, Cn. These you get by forming, so C1's a dot, C2 is the same, C3 is the same. For C4 and higher, basically you take n vertices and you simply connect them from one to another in a big long daisy chain. So C4 would look like this. And C5 would be like that. K5 would be I probably missed some. Yeah, there we go. These are undirected graphs, but you could envision directed versions of them. But for these, they're just undirected. And then there's wheels. So to find wheel n, we take cycle n and we just add one more vertex in the middle. So wheel 1 would look like that. Wheel 2, I believe, would look like that. Wheel 3 would look like that. Wheel 4 would be like that, and so on. All right, so those are some examples that we'll refer back to sometimes. All right. Next concept is subgraphs. So WF is a subgraph of VE if W is a subset of V and F is a subset of E as sets. Let's see, off topic. First 4-digit numbers, 2 prime numbers that add up to 37,998,938. Cool. Awesome. Alright, that's worth screenshotting. Well, if you did it by hand, you might be wrong, but I'm guessing you did it with code, in which case I'm guessing you're right. Cool. Yeah, this is what's fun about computers, right? You can like stick them on problems like this and they'll just happily work away. When I got my first programmable calculator, I like constantly had it doing weird calculations. I learned that the sum of reciprocals heads towards infinity, so I started adding up reciprocals to see how big I could get. It grows really slowly. But yeah, that's fun stuff. Alright, so subgraph, you basically just take some collection of vertices and edges. You have to still end up with a graph. You can't have an edge that, you know, connects a vertex that you didn't put in your subset W. But kind of the obvious way. Alright, so some operations we can do to graphs. So there's a graph. Removing an edge so if you want to remove an edge, you simply take it out of the set of edges. So if I want to remove this edge, for example, it's really just a matter of getting rid of that edge. And, you know, unless we say otherwise, our graphs don't have to be connected. So if I remove this edge, what do I end up with? You know, I end up with this graph, which isn't connected. There's no collection of edges from this vertex to that vertex, but it's still a graph. It's a disconnected graph, but that's okay. Oh, cool. We got agreement on 1039. Excellent. Yeah, so I wonder what the 5-digit cutoff is. All right. Actually, it would be cool to find like the 3-digit and the 2-digit case also. And those are quicker to find. So that's removing an edge. The other thing we can do is contract an edge. So to contract an edge, we remove the edge, but then we join its vertices. So if I were to remove this edge, right, I would take that edge out, but I would join these two vertices together. So now this edge would be connected there, and this edge would be connected there. All right. If you want to remove a vertex, typically the way we do that, we take out the vertex, and then we remove whatever edges were connected to that. So that would take out these three edges here. There's no shortest path involved in this yet. These are just straight mechanical procedures. And there's nothing terribly exciting going on with these. But as we start talking about algorithms related to manipulating graphs and analyzing graphs, we'll sometimes do some of these things, and we'll describe them again when they come up. But I just want to introduce them at this point. All right. So I haven't said this explicitly yet. I probably should have, but here's the thing: when we're drawing a graph like this or like this, right? The way we draw it on paper is pretty much irrelevant. So, you know, here's a graph. Here's another graph. They are exactly the same graph. The fact that one is drawn, you know, with two vertices on top or two vertices on bottom makes no difference. Okay? These would be exactly the same graph. And this graph is exactly the same graph as that one. I could label this, you know, A, B, C, D, and I could label this A, B, C, D, and they are completely identical. The same set of edges, the same set of vertices, the same connectivity of edges connecting pairs of vertices. Yeah, this does cause uneasiness. So one way that you sometimes think about this is you know, magnets with rubber bands between them. So you know, these are little refrigerator magnets that you can stick on a wall or something, and they've got, you know, infinitely stretchable rubber bands connecting them wherever there's an edge. Any place that you decide to put those magnets, if you were to take a picture of the result, that would be an equivalent graph. Right, so I could simply slide this C over here and slide the D over here, and this would transform into that. And here, you know, I could just, if this was, you know, ABC, and this was ABC, right, I could just take this and I could rotate it, you know, 120 degrees counterclockwise, and I would end up with this. So when we draw graphs on paper, we're doing it to, you know, sort of get an idea of something that might be going on. But the picture is not the graph, it's a representation of a graph. The graph itself is really just this notion of edges and vertices and connectivity. And so this poses the following question: how do we represent these graphs to a computer? And we wouldn't want to represent it with, you know, a JPEG of a drawing like this, because that would be a nightmare for a computer. Computers don't do images very well yet. That's still coming down the road. But computers do other kinds of information very well, in particular arrays and matrices and linked lists and things like that. So we want to take this, which is useful for humans, and figure out how to correlate this with something that's more usable by a computer. So we want to look at representations of graphs. graph representations. I knew I typed that too quickly. All right, so a couple of main ways that we're going to do this. And let me make a graph. And I'll stick with undirected graphs for a few more minutes. All right, so here's a harmless looking graph. So one approach is an adjacency list. And we simply list for each vertex every vertex that is adjacent to it. And so, for example, vertex A, which edges are adjacent to it? Looks like B and C, and that's it. Vertex B is adjacent to A and D and E. Vertex C is adjacent to A, D, and F. You can let me know if I make a mistake. D is adjacent to B, C, E, and F. E is adjacent to B and D. And F is adjacent to C and D. So how would we store this in a computer? Linked list would work, right? You could have an array of vertices, and associated with each element in that array, you would have the name of the vertex and then a linked list showing the vertices that are connected to it or adjacent to it. And that works well on a computer, and we can answer all kinds of questions like, for example, is there an edge from C to F? Well, we could go to element C and we could search that linked list for an entry F. And if we want to know, is there an indirect way to get from A to E? Well, now it gets more interesting. We know we can get from A to B, so we could say, is there a way to get from B to E? And we could check the adjacency list and say, yeah, there is. And if there wasn't, we could say, well, we know we can get from A to C. Is there a way to get from C to E? Well, C can get to A or D or F. Is there a way to get from any of these to E? And you could write a little recursive script to do that. And if you were given this list, you could draw this picture. Now, you wouldn't come up with exactly the same picture I drew, but you would draw, 6 vertices, A through F, and you would draw an edge between A and B, A and C, B and A, B and D, B and E, and so on. And you would end up with something equivalent to that graph. So this captures all the information that this picture does. All right, alternatively, we could do an adjacency matrix. And an adjacency matrix looks like this. And we simply record, a true-false flag for each row and column if there's an edge between a pair of vertices. So A is connected to B and C, and not connected to anything else. B is connected to A, D, E. C is connected to A, D, and F. D is connected to B, C, E, and F. E is connected to B and D, and F is connected to C and D. There's a matrix representation. And this is a nice matrix. This is a 1-0 matrix. This is really small to store. It's a single bit per entry. Every entry is a 1 or a 0. And if you're doing 215 or you've done 215, life gets a lot easier when you know that your matrix contains only 0s and 1s. A lot of your operations become bit operations instead of doing arithmetic. And in this case, you may notice that this matrix is symmetric. If I go to a row and a column, I find the same values if I go to that column and row. And that's got to be the case because in an undirected graph, if there's an edge from C to F, there's also an edge from F to C. That just kind of makes sense. And just like the adjacency list, we can answer lots of questions about this graph just from looking at this matrix. For example, the degree of A is just the sum of the entries in this row. That's 2. The degree of B is the sum of the entries in this row. That's 3. The degree of C is the sum of the entries in that row, and so on. In here, the degree would be the number of things in that list. Well, that's a little harder to count. You have to iterate down the list and keep track. Yeah, TI-84 is for the win. If we add up all the elements in here, what are we going to get? We're going to get twice the sum of the degrees. And that's going to tell us something about how many edges we have. And we don't really need, the whole matrix. We could just store an upper or lower triangle. But if we were to introduce directions, if these edges were directed, then this would no longer be symmetric. We could use the same representation, but where we had an edge from A to B, we might not have an edge from B to A. And that can also be captured in an adjacency list. We would have this entry here, but we might not have that entry if there was no edge from B to A. This also lets us easily capture a weighted graph, because if we put weights in here, we could simply store those weights instead of just a binary flag and capture all that information in this adjacency matrix. All right, there's another way to represent these things inside a computer. This is an incidence matrix. So let's label these. Let me just make a new graph. And let me label my edges. And so an incidence matrix, we can list vertices and edges. You don't always have the same number of edges as vertices. I just didn't get very elaborate. And we basically indicate whether each edge is incident with the given vertex. So A is incident with V and Z. B is incident with X, W, and V. C is incident with X and Y. D is incident with W and Y. And E is only incident with Z. And so that captures the graph information also. So this notion that, a graph can be drawn different ways on paper, but still be the same graph, raises the following question. How do we know when two graphs are actually the same? If we had an adjacency matrix for this graph and this graph, the matrix would be exactly the same. So it would be easy to say, yeah, these are the same graph. But suppose our vertices were labeled like that, right? This is still the same graph. The labels that I've drawn are different. And, I might call this E1, E2, E3, E4, and over here I might call this W, X, Y, and Z. But the labels don't affect the graph, right? The thing that makes this graph is that it has 4 vertices, it has 4 edges, and there's connectivity between pairs of vertices in this way. But how do we know that this is exactly the same graph? So we want a definition of this. And the terminology here is isomorphism. And once you start talking isomorphisms, you're in for a good day. So isomorphism, same shape, right? Meaning that, we can manipulate the graphs of one vertex to make it look like the other one, as long as we don't break any of the strings connecting pairs of vertices. Yeah. How many holes a straw has? Oh, like, you're talking topology. Yeah, so in topology, we look at, a coffee cup, and a coffee cup is the same as a punctured disc, right? Because if you made that coffee cup out of clay, you could flatten it down, and you'd have the handle left, and you basically have a flat thing with a hole in the middle. So being able to morph one thing into another, if you can do that, then they're called isomorphic, or sometimes homeomorphic, similar shape. So yeah, this is good stuff. So let's look at two graphs. So graph G1, which is comprised of vertices V1 and edges E1, and graph G2, which is V2, E2. So we can say G1 is isomorphic we can't spell it, but we can say it. G1 is isomorphic to G2, which we sometimes write as an equal sign with a little tilde on top. Okay, this is if and only if there exists a bijection F which maps the vertices of the first graph to the vertices of the second graph such that so what should I call these? A, B are adjacent in G1 if and only if F of A and F of B are adjacent in G2. Okay, so first of all, what's a bijection? It's a map which is one-to-one and onto. So it takes two things over here and it maps them to two things over there. And if these two things are different over here, they are different over there. Okay, so it's a one-to-one in that sense. And it's onto. Everything in G2 is mapped to by something in G1. Or in V2 and V1. Right? So it maps different things here to different things there, and it maps something to everything that you find over here. So it's a one-to-one correspondence. So if there is a one-to-one correspondence between this set of vertices and that set of vertices, and that correspondence preserves adjacency. So two things over here are adjacent if and only if f of those two things is adjacent over here. If all of that is true, then we can say that G1 and G2 are isomorphic. And it's basically saying, yeah, if I name this A, and I name this B, and I name this C, and I name this D, then adjacency is preserved, right? A and B are adjacent here, A and C are adjacent there. So in layperson's terms, if you can relabel your vertices in such a way that you end up with exactly the same graph in the traditional sense, you know, where I could move around the letters and have it look exactly the same, then the graphs are said to be isomorphic. So there's A, B, C, D, E. There's a graph. And here's another graph. Nope, that's not right. I'll do this. There's another graph. These are isomorphic. If I take E to T, if I take A to X, if I take B to Y, I'm doing this in my head. I think that will give you an isomorphism. So this bijection, right, this one-to-one correspondence between these vertices and those vertices basically tell you how to relabel this to make it look like that. Okay, so that's what an isomorphism is. Being able to tell whether or not two graphs are isomorphic, though, really hard problem. Not a problem that we have a general solution for. On the other hand, if you look at the adjacency matrix for two graphs, if I rename my vertices, if I change my vertex D to be the vertex X, right, I can apply my isomorphism, my bijection of the vertices, and relabel these to be the vertices of a second graph. Then my question is this matrix the same as some other matrix? And if I'm relabeling, you know, if I'm calling this column X and my other matrix I'm calling this column and row X, then the question is, can I rearrange the rows and columns of one matrix to make it look like another matrix? And so we can reduce this to a pure question about matrices. But that's a hard thing to, well, it's an easy thing to do. It's a computationally intensive thing to do. If you have a matrix that's 4 by 4, how many ways could I rearrange the rows and columns of that matrix? Well, we just did this. I can take this first column and I could choose to put it in either the first, second, third, or fourth column. So there's 4 ways to do that. And once I've done that, I can take the second column and I can choose to place it in one of 3 remaining columns. And this third column I can put in one of 2 remaining columns, and then this fourth column will have to go where it ends up. So for a graph with n vertices, I have n factorial possible rearrangements of that matrix. And that's computationally painful. Right? If you have 1,000 nodes in your graph, 1,000 factorial ways that you could try renaming those to compare it to another graph's matrix to see if it's the same matrix. That's really not tractable. So how do we know if two graphs are the same? Well, we don't. There's not a good way to do this, but there is sometimes a good way to tell the two graphs are not the same. So there's things called graph invariants. I love typing without seeing what I'm typing. It's always like a surprise. So graph invariants are preserved across isomorphisms. So the shape of a graph, or whether or not any edges cross over each other, these have nothing to do with the graph itself. We can have two graphs that are isomorphic, and in one of them we might have edges crossing each other, and in the other one we don't. And we can't simply say, oh, no edges cross, here's some edges cross, they're not the same. That's not invariant under these isomorphic transformations. But there are some things that are invariant. For example, the number of vertices. No matter how we rearrange one graph into an isomorphic graph, the number of vertices will not change. Neither will the number of edges. Neither will the sum of the degrees, which we know because that's related to the number of edges, right? Also, if we were to look at the number of vertices with certain degrees, that will not change. So if we tally a list of the degree of each vertex and we find that our vertices have degrees, 2, 4, 6, 1, and 5, in any graph that's isomorphic with 5 vertices, we're going to find that one of those vertices has degree 2, another has degree 4, 6, 1, and 5. And so these can help us start to discover some ways that we could at least recognize when two graphs are not isomorphic, right? When they can't possibly be isomorphic. For example, if my other graph has a vertex of degree 3, it can't be isomorphic to this graph if my original graph did not have a vertex with degree 3. And so we can start writing some code to use those kinds of characteristics. But in general, it's a hard question. All right, so we'll stop there for now. So Wednesday, we'll talk about the homework you just turned in, and we'll start looking at paths, which is basically what you get when you start at one vertex and by following edges go from one vertex to another to another. That's a path. And we'll start looking at types of paths, when paths exist, and we're working up towards trying to find shortest paths from one point to another. All right, cool. Oh, someone got to 92 million. Cool. Awesome. All right, cool. Have a good one. I will see you next time.